Hello, students. So what I wanted to do today in this video is start showing you labs that effectively, here's the problem. I can show you a simulation, but you might say, well, of course it looks like that. That's what's programmed to do. How do I know that's actually the real world? And I can't send y'all lab equipment at home. And I've done my best to give you labs you can do on your own. But we're at the point where you need to at least see the lab perform. So I'm going to demo it. I'm going to actually do the lab in front of you, and you're going to take data. And then you're going to do the calculations to understand what's going on. Now, yeah, I'm doing this in one take. There's no trickery. We're going to have a stopwatch and whatever other equipment we need. If we need sensors, we'll have that available. But this is the Atwoods machine lab. We're going to start with that one. Right, so Atwoods machine, and there's stuff to write down. I don't know if that's flipped for you. I don't think it is. I need to tell you what an Atwoods machine is. An Atwoods machine is effectively a pulley with two weights on the end. So there's the two weights. And here's my pulley. It's actually got two wheels because I don't want it to get tangled up and bang into each other. The idea is that we're avoiding problems with the setup getting tangled like I just tangled it. Right. So one of these is going to be the setup that has extra weight on it. At the moment, they don't have extra weight. I can hang the pulley, hang the weight from the pulley, and I can set it at any position, and it should, other than oscillate, it shouldn't move up and down. And I can change the height. It's stable, right? And so this is a bit where I need a little bit of marker. Give me a moment. There's the pause button. So what's happening is on one weight, I have a tension upwards and a weight downwards. And the weight is mass times g. So g is a vector. So we have that written in. And I understand it's not exactly 100% viewable, but that's okay. All right. We have a tension upwards and a weight downwards. Now, on the other side, we have exactly the same thing. Right? As we have a tension upwards and a weight downwards. And note that I put different M's, one big and one small. In your lab, I believe this is called M1 and M2. Right, they're just different. But at the moment, they're not different. And I want to show you what happens when they are. What happens when they are, if I take and add 10 grams of weight to it here, they slowly fall. You can see one fall, and you can see the other one rise until they hit the ground and then is stationary. I've set some wires and stuff here. So the idea is we're going to properly do this measurement a few times with different weights, and we're going to figure out what's going on here. Right now, there is an obvious thing. I can take a weight and I can just drop it, and when there is no tension involved, it just falls. Right? It's just gravity. And so you know the acceleration from that. That's 9.8 meters per second squared. But when it's just an unbalanced system like this, it's not necessarily clear what the acceleration should be. But it's not too terribly difficult to work out that the acceleration has to be due to the net force on each of these weights. One of them, the tension, well, in all of them, the tension is the same because it's the same piece of string going over the pulleys. So this tension in these strings should be the same throughout. But in one of these, what we have is we have what am I thinking of? In one of these, what we have is the weight's a little bit larger, and so there's a net acceleration downwards. There's a net force downwards. And the other one, the weight is a little smaller than the tension, and there's an acceleration upwards. They're the same acceleration. So there should be some acceleration due to these excess weights. And so what we have is, on here, we have the 200 grams that are listed in the lab on each side. And we have 10 and 20 gram weights waiting to go. And we're going to time this. Now we're going to time it from when it starts up here to when it hits the floor down there where the other weight is. All right. So this is probably going to be the view that we need for a little bit, but what I also need to do is measure this distance. Because the idea is we can just time it and get the acceleration for an object falling. But we need to know some information from it. Now obviously, since I've just gotten a 2-meter stick, you know we need the distance. But if we write this out kinematically, what we should have is delta x is something, v initial is 0, v final we don't care about, the acceleration is what we want, and the time is going to be measured. So we're going to calculate based on this. We'll eventually get delta x is 1/2 at squared. So we can solve that for the acceleration once we know the time and the distance. Now, I had to make a 2-meter stick, and I've got it upside down. This is going to be the same for all the measurements. But if I bring it in here, I'll show you that that is I believe it is right at 1.5 meters exactly. Could I have done that any better? Maybe. That was just gambling and setting it up. I did not measure that beforehand. So your distance is going to be 1.5 meters instead of a question mark. All right, and then what we're going to do is repeat this measurement several times for the different masses that we have and for this distance. All right, so on one side you'll have 210 grams to start with, so 0.21 kilograms, and 200 on the other side. Okay, so in your blanks, M1 should be 210 and M2 should be 200. So I'm going to put the weight on here. You'll see it starts to move, but I'm going to set it back. When I let it go, I'm going to start the clock. It's in my hand. And then we'll see it hit the ground. 3, 2, 1. All right, see it moving. I'm going to point at the ground. 6.35 seconds. All right. Now we're going to try that again. We're not going to trust, someone that's doing this. We're going to make sure we got the right time. Because I was doing a bunch of stuff moving around. So, we'll do it a couple times, make sure our technique is proper. So, we're resetting. 3, 2, 1. And it starts moving. You see the bottom weight rise. Now you see the top weight, 6.38. Either one of those are fine. All right, that tells us that we probably got the numbers that we want out of it. All right. So you'll notice I keep dropping the weights here. I keep slipping off this loop. That tends to be a problem, and that's okay. All right, so one of the things you can do if that's a problem is make sure that your loop is tight on your weight. So if you're ever doing this in, I don't know, maybe you have some universities like to make sure that students take multiple goes, at physics. They want them to take their physics. Now, I realize what's going on here. We needed to do this 10 times for each one, but I do want you to see this time that it's a little different. So we're resetting the clock. I want to start it. 3, 2, 1. You might hear that beep. That time I got 3.25 seconds. So this is what we're going to do. We're just going to take data like this. So you're going to see my shoes and these different weights. But you're always going to see that one weight is touching the ground, and we're going to time how long it takes for the other weight to slip down. How do you do that? That's weird. All right, anyway, that'll do. All right, so we'll have our clock. All right. You'll see me start it. 3, 2, 1. I stopped it early. You got to be careful of this stuff. So this is going to take a little while. Understand that there's going to be some data here that's a little weird. Let me pause for a moment. Okay, so sometimes you have some weird problems come up, like someone emails you from vocabulary.com. I don't understand what that is. That's okay. So we've got our weight set up. All right, this is the 10 gram extra, the 10 gram excess. We're going to do 10 trials of this. Actually, we've done, I think we've done 8, but we're going to do 10 again. So you get we've done 2 already, but you're going to get 10 more. And we're just going to repeat this 10 times, and I'll show you the time each time. Okay? And then we'll do this, again, 10 more times with the other ones. All right, so 3, 2, 1. You see one start to go, the other one come up, and 6:13. Now, there's a reason I'm asking you to do the averages notice last time it was like 6:38, now it's 6:13. And again, you can tell this is 6 seconds. So, all right, so we'll do it again. Clear. 3, 2, 1. And you see one rise and the other fall. 6:22. I'll tell you what I'm going to do, and we're going to cut these to 5. You only need to do 5 trials on average. All right, if you're listen to Rife, at some point he said something about measurements that 5 was enough. And that makes sense to me. So 3, 2, 1. So you might notice that if you watch the video close enough, I might be making errors or something. 581. Right, so we reset it. Last one was 581. This one, 3, 2, 1, go. Nope, I screwed it up. 3, 2, 1, go. $6.19. So we'll do this 2 more times. There is one thing. When I let it go, it's obvious that I know when I'm letting it go, so my nerves can act to preempt it, to hit the button before I drop it. When I'm seeing it hit the ground, I got to see it and then hit the button. So there's a delay. There's probably a 1/10 of a second delay there, if not, So anyway, 3, 2, 1, go. I botched that. That would have been 6:52, but we're going to reset and do that again. 3, 2, 1, go. It's running, it's going. Hurry up. 6:22. So one more time. Now, if you've taken careful measurement of these, you only need to do 5 trials. That's all we're going to count, but you can find the data in here and get the 5. So 3, 2, 1, go. That one said 663. We've had a couple of outliers, so I'm going to do one more. I think that one's fine. I watched it, but sometimes you just get a weird one. So 3, 2, 1, go. Six even, 600. All right, so hopefully that worked okay. Now, if there's any issues, feel free to be like, hey, you didn't show the time for enough time, or you didn't, you should be pausing the video as you do these. So what we're doing is we're taking our 10-gram mass off. We're going to put our 20-gram mass on and do 5 trials. Right, so we have our weight up here. We're just going to secure it so it doesn't slip off. And there's a trick. So I don't know if anyone was in the Boy or Girl Scouts, if they still teach like knots and knot tying and such, but there is a trick to making sure that things don't break, that don't fall apart. So this one, your large mass is 220 grams, and your small mass is 200 grams. And the small mass is on the ground now. It's still 1.5 meters. And we're going to run this here. So 3, 2, 1, go. That one was much faster, and it was exactly 3 seconds. So that was trial 1. Trial 1 is 3 seconds. And we'll do trial 2. And I only want you to use 5 of these, but we'll try to do it 6 or 7 times in case there's like a wide outlier. So 3, 2, 1, go. 307. 307. So you can tell these are getting faster. You can probably guess that when I add the 30 grams on, it'll be about 2 seconds. So 3, 2, 1, go. 331. 3.31 seconds. Can you see? There's a glare. How is there a glare in this room? Their windows are closed. Anyway, I'll do it again. This is trial 4. 3, 2, 1, go. 319. 3.19 seconds. So we'll do it again. 3, 2, 1, go. 319. 319. And I notice I do have to be careful not to do one obvious mistake, which is watching the video instead of the weights. But so far I haven't messed anything up. So we'll do this one and one more. 3, 2, 1, go. 319. I'm hitting that number a lot. Your averaging will be very straightforward, I hope. All right, last time with this. 3, 2, 1, go. 325. 3.25 seconds. All right. So we can now reset. We can do the third trial, which is going to be, and you see the weights fall off again. We're going to do one mass is 30 grams heavier than the other. So we'll have 200 grams and 230 grams. So we'll secure these on there so they don't slide off. And it takes a little bit of twiddling the string to make sure it doesn't slide off. Students have this problem of their big weight slides off. And when it does that, everything goes all to hell. So, you get weights flying around the room and you shouldn't. So we'll do this once without timing it, just so you see it's faster. There you go. All right, you can see that it's not quite 3 seconds. It's probably closer to 2. All right, so we're going to do 6 or 7 trials of this. Take 5 of them. Right. So 3, 2, 1, go. And something broke on the timer that it didn't reset. So we're going to run that one again. This happens. I'm using a cheap, like a 20-cent timer. So we're just going to be careful and do this again. 3, 2, 1, go. 2.37 seconds. 2.37 seconds. 2.37 seconds. So we reset. 3, 2, 1, go. 2.56 seconds. 2.56 seconds. So 3, 2, 1, go. 2.41 seconds. 2.41 seconds. And the computer fell asleep, so let me wake it up. Your teacher can't keep the computer working. All right, so we got the computer working again. This is going to be trial, I believe this is trial 4. So we'll do 4 more. 3, 2, 1, go. 2.60 seconds. And you can tell now that the more that we do this, and the more weight we've added to our heavy weight, the less accurate the time is. As that our first one is almost certainly going to be better measurements just because it took 6 seconds. The error in here, in me taking the time, is probably 0.5 of a second. It's like 0.05 of a second. And so that's a significant more part of this than it is of the slower one. All right, so this is trial 5. 3, 2, 1, go. 2.44 seconds. By the way, this is a technique you could use if you're doing science fair and you're doing something where you have to do timing. It doesn't hurt to video it because you can always go back and review the video. All right, so trial 6, 3, 2, 1, go. Nope. Sometimes you double hit the button and it breaks. So 3, 2, 1, go. I hit it early. I've not got good viewing today for whatever reason. 3, 2, 1, go. 2.53, 253. Again, 253. All right, so this is trial 7. This is the last one. 3, 2, 1, go. Didn't stop. Still not stopping. What's wrong with this thing? All right, next time we'll have a proper stopwatch. 3, 2, 1, go. 2.40, 240, 2.40. Now, I've taken a lot of your time. That's 25 minutes to do this lab. I apologize for it. I hope that, you get the gist of data taking and the idea that as you're doing a lab, you want to be efficient at doing the lab. You don't want to sit there and, when you come in spring semester, you've got 2 hours to do this. And here it took me 25 minutes, not counting how long it took to set everything up and draw pictures that you needed, and every time I paused the video. So just be aware is that you got to be efficient when you're doing your work. All right, so that said, we've done 3 different types of trials where we took data. Now, on the other side, I've given you one answer, is the kinematics to find the acceleration from our time. Now, in the other thing, we can try to get the acceleration, a theoretical acceleration, from what are the forces on these masses. All right, I've talked about the weight force. I've drawn it up here. There's a weight force, and there is a tension force in these ropes. And they're not equal, right? On one side, on the heavy side, the weight is slightly more than the tension, and so the weight falls. And on the other side, the tension is slightly more than the weight, so the weight rises. But those tensions are equal because it's the same piece of string. So both masses are effectively tied together and they're accelerating. And from these, you can write out your sum of the forces. And so on this side, sum of the forces on mass 1 is going to be, well, we're going to take up as positive here. So we'll have tension minus mass 1 times g. But on the other side, right, basically what we're saying is up the rope on this side is positive, which means down the rope on the other side is positive. So we'll take plus y. This is what's called wraparound coordinates, is it wraps around the pulley. So what we mean by positive motion here is motion where mass 1 goes up, and that's positive, but that means mass 2 goes down, and that also is positive. So sum of the forces on 2 is going to be mass 2 times g minus the tension. And from that, both of those have to equal a mass times the acceleration. You can build an expression that only has the acceleration in g in it. And then we ask you some questions in the lab like, what set of data worked best? Should I use a small mass or big mass difference? Which thing's theoretical, which thing's actual? And if you're watching the video carefully, I'm telling you this stuff. And then finally, a more useful point of this, not exactly useful, but more useful. When you did the free fall measurements, in principle, you could measure g from it. You just measure the acceleration of the thing falling. Here, we can slow down, so we can measure the acceleration of a slowly falling object, but where the main thing occurring is the gravitational force. And that lets us calculate g with more precision, let's say. I'm not going to argue that it actually is precise. If you get a number between 0 and 20 for g, I will be happy. But I do ask you to calculate a percent error. And I give you the expression for percent error. Your expected value is 9.8. But your observed value is whatever you got out of this using the actual, the 1/2 at squared acceleration, and plugging that into your F equals ma formulas. All right. So that's a 30-minute video on this lab. I've got a bunch of these to do, so we're going to stop it there.